Here's an interesting organic reaction that's widely taught, and you might even find it on an exam like the MCAT exam because it involves some very interesting reasoning to explain the result. When 1,3-butadiene is treated with HBr, two products result. Both of these products involve formation by addition of a proton to the terminal carbon of the 4-carbon pi system. So here's that proton that added. And for this product, it involves 1,2 addition, and here's the proton in this product, and the nucleophile is added at the other end, so it's called 1,4 addition because it involves addition to the 1st and 4th carbons of the pi system. So using our arrow pushing, we picture a pair of these pi electrons being used to form a bond with this proton, and this pair of electrons stays with bromine to form bromide. This forms an allylic carbocation, which is resonance stabilized. We picture this pair of pi electrons moving over here to leave a positive charge on the end carbon. And thinking of reaction of bromide, which was formed in the first step, with these two carbocation resonance structures, you picture bromide donating a pair of electrons to form a sigma bond. And the same thing is true over here. So electrophilic addition, protonation, at the end of a pi system forms an allyl carbocation that's resonance stabilized, so the bromide can add at either one of the ends of the 3-carbon allylic system. MO theory leads us to the same conclusion. The allylic carbocation has 2 electrons. They're in pi 1, the bonding MO, and the positive charge is in pi 2, the non-bonding MO. This non-bonding MO looks like the middle graphic here, so we see that the positive charge is at the ends of this pi system and never in the middle. So bromide will react at the ends of this allylic system. And of course, we also notice that this allylic pi system is more stable because the 2 electrons in it are both in a highly stabilized bonding MO. So either picture, the MO picture or the resonance picture, gives us the same conclusion. The reaction will be at both ends of the 3-carbon allylic pi system. It's also worth pointing out that the formation of the allylic carbocation, as I've shown in the top row here, with the pi electrons reacting with the proton, and these electrons staying with bromine to make bromide, occurs at the end of this 4-carbon pi system. Alternatively, we could picture protonation at the 2nd carbon end. But protonation at the 2nd carbon doesn't give us a resonance stabilized carbocation. And the MO picture wouldn't show us a particularly stabilized MO for the pair of electrons. So, we can easily account for the regioselectivity. Protonation is highly preferred at the end, where we form an allylic carbocation. But there's something else interesting about this reaction. The ratio of the products formed by 1,2 addition and 1,4 addition depends on the temperature that the reaction is run at. Look at these results. At minus 80 degrees, the ratio of the products is 81 to 19, favors the 1,2 addition. At this very cold temperature, this reaction is irreversible. And you remember that under irreversible conditions, the ratio of products will be determined by what's called kinetic control, simply how fast the products are formed. At warmer temperatures, the 1,4 product is favored. Only 15% is the 1,2 product, and 85% is the 1,4 product. The explanation is simple. At 45 degrees, the reaction is being run under reversible conditions. As we follow the reaction with arrow pushing, the allylic carbocation is formed as the bromide leaves from the HBr. Once the carbocation is formed, it has 2 resonance structures. Bromide can add either to this carbocation or this resonance structure at the other end. Formation of the 1,2 product is faster, but makes a less stable product. Formation of the 1,4 product is slower, so we see less of it under irreversible conditions. But when we have reversible conditions, and this bromide can leave again and reform the carbocation at the higher temperatures, ultimately it's not the faster formed product that dominates, but we have a predominant amount of the more stable product. This can be nicely summarized in an energy diagram. The butadiene is protonated to make an allylic carbocation. And the activation energy to form the less stable 1,2 product is smaller, while the activation energy to form the more stable product is greater. So it's formed more slowly, but under reversible conditions, eventually the more stable product will predominate. So the conclusion, at minus 80 degrees, the faster product is favored. We have kinetic control, irreversible conditions. But at warmer temperatures, the more stable product is favored because we have thermodynamic control under reversible conditions. 1,4 addition of HBr to dienes is a classic case of kinetic control versus thermodynamic control in its relationship to temperature.